Hello everyone, welcome to today's class. So this is probably the last class we will be having in the current session of solving the GATE previous year question papers. So just to revise what we are doing, we were so in the starting of the session one we started with heat transfer subject, then we covered the process control and instrumentation subject. Basically we are solving the past years GATE questions that have been asked. So we are providing these video solutions that will be ultimately available on the NPTEL Gate website, and during this online live sessions, we are sharing this video solution. Meanwhile, if you have any doubt, you can ask the doubts or clear your doubts with us. So right now we were looking on this fluid mechanics subject. So we covered the basics concepts behind the fluid mechanics and what the subject covers. So the subject deals with the study of the behavior of the fluid either at rest or in motion. So in this specific subject, we are covering the concepts of fluid statics and motion, including the governing equation that describes the basic principles. So these basic principles includes the Newton's law of viscosity or the power law model. Based on this power law model, we can find this parameter n, based on which we can comment on the rheological nature of the fluid. So whether the fluid is rheopeptic, pseudoplastic, what kind of nature is fluid. So while solving the questions, we saw that the questions related to commenting on the rheological behavior of the fluid are very frequent. So using the power law model, we can find the viscosity and then we find the viscosity of the fluid. So that question was also very common. Then we looked on the pressure drop calculations for tubular flow, and so we used the equation of continuity, Bernoulli theorem, all those in this pressure drop calculation for tubular flow. And today we will be again seeing the instrumentation related to this flow measurements. So basically they will be measuring the pressure drop across a certain section, and based on that we can find the flow velocity or the flow rate of the fluid. Later on in today's class we will be seeing the flow impact beds of solid particles. So today we will be covering this flow impact bed of solid particles. This you might have also covered in mechanical operation subject. So today we will be covering questions related to Venturi meter. So these are basic simple questions that only involve the use of certain formulas governing the Venturi meter. So then there are a few more questions related to Venturi meter. Then we will be solving the questions related to this packed bed or fluidization velocity, all those numericals. Then again, this is related to settling velocity or the flow of the particle in the fluid or the free settling velocity of the particle. Then these are the questions related to packed bed. Then these are general fluid dynamics questions. And again, this involves calculating the pressure drop across the packed bed. Then flow measurement devices. Then these are the applications of the Ergun equation that governs the flow through packed bed or the pressure drop through the packed bed. So that is our plan for today's class. So let's start with today's class. So we are starting with question number 52 of GATE 2022. In the question states a venturimeter with venturi coefficient CV is equal to 0.098 is connected to pipe of inner diameter 50 mm. Water with density of 1000 kg per meter cube is flowing through the pipe. The pressure drop measured across the venturimeter is 50 kilopascal. If the venturi throat diameter is 20 mm, the estimated flow rate of water is dash into 10 raised to minus 3 meter cube per second. So let's say if we are having a certain pipe and we have to measure the flow rate through the pipe, so we can use different instruments. So one such instrument is venturimeter. Another such instrument to measure the flow velocity is spider tube. So in venturimeter we are having this kind of conical cross section which are connected together. So this section is known as the throat of the venturimeter, for which we have been given the diameter as 20 mm. So ultimately this section, that is known as venturimeter, is placed inside or fitted inside this pipe, and what we will be doing is we will be measuring the pressure drop across both of this section, that is delta P, and based on this pressure drop we are having we can use the Bernoulli's theorem to find the flow rate. So ultimately we will be having the flow rate as a function of pressure drop and this diameter of the venturi and some other factors. The main factors governing the flow rate are the pressure drop and the diameter, throat diameter or the diameter of the pipe, that is this diameter. So let us take on a look on the video solution for this question. So so we have to find Q for the given venturimeter. So for the venturimeter, we can write the average velocity V as CV, that is basically venturi coefficient, upon under root of 1 minus beta raised to 4, where beta is the ratio of diameter, basically smaller upon larger diameter, into under root of 2 times the pressure drop delta P upon rho. So over here, we have been given that the venturimeter is connected to a pipe of inner diameter 50 mm and the venturi throat diameter is 20 mm. So that is basically beta is 20 upon 50, that is 2 upon 5. And pressure drop we have been given as 50 kilopascal and density is 1000 kg per meter cube. So we will replace all those values in this venturi equation. We will be getting CV is 0.98 upon 1 minus 2 by 5 raised to 4 into 2 into 50 kilopascal is 50 into 1000 upon density is again 1000. This will get cancelled out and we will be having 0.98 into under root of 100 will be 10 upon, so this denominator will become 0.9744 and this will be equal to 9.928. So the average velocity is 9.928 meter per second. And since we have been asked to find the volumetric flow rate meter cube per second, we can just multiply this into area. So Q will be area times of V. Area is pi by 4d square. So the diameter that is to be considered is the diameter of the venturi throat. So it will be 20 into 10 raised to minus 3 meter whole square into 9.928. So you can calculate this, and this will come around 3.119 into 10 raised to minus 3 meter cube per second. And in the question, we have been asked to find the estimated flow rate into 10 raised to minus 3 meter cube per second rounded up to 2 decimal places. So we can just write it as 3.12 into 10 raised to minus 3 meter square per second inverse. So the final answer, we can write it as 3.12. So in this question, we saw a simple application of the venturimeter, whereby we were asked to find the flow rate. We were asked to estimate the flow rate passing through the pipe. Then another such equipment to measure the flow rate is the pitot tube. So basically, this is a very straightforward question which asks pitot tube is used to measure gas. So option A is liquid level in tank. Option B is flow velocity at a point. Option C is angular deformation, and option D is vorticity. So what pitot tube does is consider a flow passing through this fluid. So what we can do is we can simply insert a tube, and then it will again calculate the pressure drop, and based on that pressure drop we can find the flow velocity at the point. So ultimately we can, if we have flow velocity, we can measure the flow rate also. So basically these pitot tubes are used to measure the flow velocity or the flow rate at a point. So one thing to notice is pitot tube are used to for point measurement. So what it will do is it will just calculate the flow rate at this point, whereas in case of venturimeter it calculates the flow rate, it calculates the average flow rate throughout the pipe. Since it takes into consideration the average cross section of the pipe, venturimeter calculates the average flow rate through the pipe, whereas this pitot tube will give us the flow velocity at a single point, so only at this point. So it might happen that the flow velocity at this point is different. So the pitot tube will only account for the flow velocity at which it is inserted. So that is, pitot tube is used to measure the flow velocity at a point. So option B is the correct option. Now, similarly, this is another question related to venturimeter. So I will just read the question and we can. Okay, so I will read the questions. So a venturimeter is installed to measure the flow rate of water in a 178 mm diameter pipe. The throat diameter is 102 mm. The differential pressure measured across the manometer is 154.3 kilonewton per meter square. The data given are dash, and find the volumetric flow rate. So in this question, similar to the previous question, we have been given a pipe for which the diameter is 178 mm. Then the throat diameter of the venturimeter is 102 mm. So this throat diameter for venturimeter is 102 mm. Then the differential pressure is measured using the manometer. So let's just consider a manometer that has been connected through pipe across both of this section. So this manometer will measure a pressure difference of 154.3 kilonewton per meter square, and then we have been asked to find the volumetric flow rate, that is Q. So in the earlier question, we saw that the flow velocity is given by this CV upon under root of 1 minus beta raised to 4 upon 2 delta P by rho. So similarly, to find the volumetric flow rate, we can multiply this velocity in meter per second by the cross section area. So that is simply we can multiply to get the fluid, we can multiply this by velocity and get the desired answer. So this question is very similar to the previous question that we saw. In this question also, we were asked to find the flow rate for the given conditions. So one another thing to note is to calculate the area. So basically we are measuring the flow rate through the venturimeter. So we have to consider the throat diameter. So this diameter should be used to calculate the area, that is pi by 4 d square, not the pipe diameter. So we should not be using this pipe diameter to calculate the area for calculating the flow rate. We should be using the throat diameter, that is in this case the 102 mm. Yes, that is what we had done in this solution. Now again, let us take a look on the next question. So this is question number 8 from GATE 2017 chemical engineering paper. So in this question, we have been given that in a venturimeter, delta P1 and delta P2 are the pressure drops corresponding to volumetric flow rates Q1 and Q2. If Q2 by Q1 is equal to 2, then delta P2 by delta P1 is equal to dash. So here we have been given two scenarios. For case 1, we have been provided that if delta P1 is the pressure drop, then the corresponding volumetric flow rate is Q1. And if delta P2 is the pressure drop, then the corresponding volumetric flow rate is Q2. And then we have been given that Q2 upon Q1 is equal to 2, and we have been asked to find delta P2 upon delta P1 is equal to question mark. So again, if we take a look on the equation governing the venturimeter or the flow rate through the venturimeter, then we have this equation Q is equal to, let's call it area, into velocity, and velocity is given by CV upon under root of 1 minus beta raised to 4 upon 2 delta P by rho. So here we have been given that in a venturimeter, delta P1 and delta P2 are corresponding at the pressure drops corresponding to volumetric flow rate Q1 and Q2. So we are considering the same pipe in this section, and the venturimeters are also same, only the flow rates are changing. That is this area, this venturi coefficient, the ratio of throat diameter to the pipe diameter, that is beta. All these parameters will remain same. The fluid density will also remain same. So ultimately we can see that the flow rate is directly proportional to under root of pressure drop. So since we have been asked to find delta P2 upon delta P1, we can write this as Q2 by Q1 is equal to delta P2 by delta P1 whole under root from this equation. So delta P2 upon delta P1 will become square of Q2 by Q1, and Q2 by Q1 we have been given as 2. So the ratio will be 2 square, it will be 4. So the ratio of delta P2 by delta P1 for the given question will be 4. So the final answer you can simply select as 4. Now let's take a look on these questions related to flow through the packed bed. So in the questions that we will be discussing now, what we will be having in most of the questions is, we will be having, let's consider any vessel of cylindrical shape. Then we will be having a packed bed which can be filled with any kind of packing, either spherical or some another shape. And then if we pass any fluid from the bottom, then at certain velocity this packed bed will fluidize, that is, these particles will start to flow. So that velocity is known as minimum fluidization velocity, and that condition is known as onset of fluidization or incipient fluidization. So in most of the questions we will be asked to find the pressure drop per unit length across the bed for at the onset of fluidization. Then we can be also we can be asked to find the minimum fluidization velocity, that is VMF or delta P by L. So this flow through the packed bed is governed by Ergun's equation that basically correlates, that is basically used to find the pressure drop across the bed for different scenarios, and it will account for kinetic losses. So it will, this pressure drop will be basically the sum of two term, viscous term plus kinetic term. So if the flow is laminar flow, then the viscous term will be dominant, and if the flow is turbulent flow, then we can say that the kinetic term will also come into play. So this was just some basic theory that we will be looking on. So let's take a look on. So let's take a look on this question from GATE 2011. So these are type of common data questions in which we have been given this data, and based on these questions we have been asked two questions which we have to solve using the given information, given common information. So in this question we have been given that for a liquid flowing through a packed bed, the pressure drop per unit length of the bed, that is delta P by L, is given by this equation. So where V bar is the superficial liquid velocity, epsilon is the bed porosity, dP is the average particle size, phi s is the particle sphericity, rho f is the liquid density, and mu f is the liquid viscosity. And for this given system, we have been given this value, that is the particle diameter is 10 raised to minus 3 meter or 1 mm. The particle sphericity is 0.8, density of fluid, that is rho f, is 1000 kg per meter cube. The viscosity of the fluid is 1 into 10 raised to minus 3 kg per meter per second. Then particle density is 2500 kg per meter cube, and acceleration due to gravity is 9.8 meter per second square. So this is the common data, and based on that we have been asked this first question. So this first question states that when V naught bar, that is superficial velocity, is 0.005 meter per second, and epsilon, that is bed porosity, is 0.5, which one of the following is correct value for the ratio of viscous loss to kinetic energy loss? So in the first question we have been asked to find the ratio of viscous loss to kinetic energy loss, whereas in second question we have been asked to find, on further increasing the V naught bar, the incipient fluidization is achieved. Assuming that the porosity of the bed remains unaltered, the pressure drop per unit length in Pascal meter under incipient fluidization condition is dash. So in the first question, we have been asked to find the ratio of kinetic to viscous loss, whereas in the second question, we have been asked to find the pressure drop per unit length at incipient fluidization. So we will be taking a look on the video solution for both of these questions. Number 48 and 49 of GATE 2012 chemical engineering paper. Liquid flowing through a packed superficial liquid velocity and mu f density, which is when V naught is 0.005 meter per second and epsilon is 0.5, which one of the following is correct value for the ratio of viscous loss to kinetic energy loss? So in the question we have been given the pressure drop equation, that is 150 V naught bar mu 1 minus epsilon square upon pi square dp square epsilon cube plus 1.75 rho V naught square 1 minus epsilon upon epsilon cube pi s and dp. So the first term you can see that the viscosity is present. So this, the first term, the we can call it as viscous loss. So the first term accounts for the viscous loss, and the second term you can see that we are having the velocity square. So basically that accounts for kinetic energy loss. And in the question, we have been asked to find the ratio of viscous loss to kinetic energy loss. That is basically the ratio of the first term to the second term. So we can write the ratio as 150 to V naught R mu 1 minus epsilon square upon pi square dp square epsilon cube upon 1.75 rho v bar square 1 minus epsilon on pi s dp epsilon cube. So let's just cancel all the common terms. So we will be left with the ratio as 150 mu into 1 minus epsilon upon 1.75 rho. Then we are having this phi s dp and this superficial velocity v naught. Phi s dp and v naught. That is, we can write the ratio of viscous loss to kinetic energy loss as 150 mu 1 minus epsilon upon 1.75 into rho phi s dp v naught. Rho phi s dp v naught. Now we can replace all the values given in the question. So 150 into viscosity, mu is given as 10 raised to minus 3. 1 minus epsilon we have been given as 0.5 on 1.75 rho phi s and dp we need. So rho is 2500. So rho we need the density of the fluid. So rho f will be 1000 and dp is 10 raised to minus 3. Phi s is 0.8. That is 1000 into 0.8. Diameter was 10 raised to minus 3. And the superficial velocity v bar, v naught bar we have been given as 0.005 meter per second. So we can calculate this, and this ratio will come around 10.714. That is, for the given system, the ratio of viscous loss to kinetic energy loss will be 10.71, and we can select option C as the correct answer from the given options. Now from the same data, we have been asked this question number 49, which is on further increasing the V bar, incipient fluidization is achieved. Assuming that the porosity of the bed remains unaltered, the pressure drop per unit length under incipient fluidization condition is dash. So this states that we were having a packed bed, and then on increasing the velocity until a certain point, that is after a certain point, this incipient fluidization is achieved. That is, the packed bed will become fluidized, and we have been asked to find the pressure drop per unit length under the incipient fluidization condition. So at this incipient fluidization condition, we can write the pressure drop across this bed of length L as delta P by L is equal to G 1 minus epsilon rho P minus rho F. Can again replace all the values. G we were given as 9.8, epsilon. The porosity of the bed remains unaltered. So earlier it was 0.5. So now also it will be 0.5. The density of the particles we were given as 2500. The density of the fluid we were given as 1000. So that is, we can write this as 9.8 into 0.5 into 1500 this will become 7350. That is the pressure drop across the bed at incipient fluidization will be 7350 Pascal per meter. So from the given options, we can see that option B is the correct answer. So we can select option B as the correct answer. So in this question, we saw how to calculate the pressure drop across the packed bed. So at incipient fluidization, what we can do is we can simply equate the pressure drop, and we have this simple equation that is given by delta P by L is equal to G rho P minus rho F. So basically, we are having this equation for incipient fluidization where epsilon is the bed porosity, and if the bed is not in incipient fluidization condition, that is it has been completely fluidized, then in that case we have to use this equation to calculate the pressure drop. That is, if we aren't given incipient fluidization or the onset of fluidization, then we have to use this equation to calculate the pressure drop throughout the bed. And in this, we saw that the first term contributes to the viscous loss, whereas the second term contributes to the kinetic loss. So most of the questions related to the packed bed will revolve around using this equation and incipient fluidization equations. So just to show a few more examples. This is again a very similar question in which we are given that a vertically held packed bed has a height of 1 meter and a void fraction of 0.1 when there is no flow through the bed. The incipient fluidization is set by injection of fluid of density 1 kg per meter cube. The particle density of the solid is 3000 kg per meter cube. The acceleration due to gravity is 9.81 meter per second square. The pressure drop across the height of the bed is this. So again, in this question, we were given a packed bed, and then we have been given that the fluid of density 1 kg per meter cube is flowing, and at the onset of fluidization or the minimum fluidization, we have to ask the pressure drop. So again, we can simply straight away use the equation delta P by L is equal to G into rho P minus rho F, and then to account for the porosity, we can use this 1 minus epsilon. So this question is again straightforward application of this equation, very simple. So this was asked in GATE 2020, question number 46. Very similar question was asked in GATE 2015. So it was question number 22. And in this also we have been given a cylindrical packed bed of height 1 meter is filled with equal sized spherical particles. The particles are non-porous and they have a density of 1500 kg per meter cube. The void fraction of the bed is 0.45. The bed is fluidized using air of density 1 kg per meter cube. If the acceleration due to gravity is 9.81 meter per second square, the pressure drop across the bed at incipient fluidization is this. So again, this is a very similar question to the previous two questions we are solving that simply involves using this condition for this incipient fluidization using this equation to calculate the pressure drop. So since these are very similar questions, we are not solving this by the video solution. Now next we can take a look on this equation which involves this resettling or the flow of solid particles through the fluid. No, we can take a look on one more example related to packed bed that involves calculating the minimum fluidization velocity. So this is question number 32 from GIT 2012. So here it has been stated that a bed of spherical glass beads of density 3000 kg per meter cube, diameter 1 mm, bed porosity 0.5, is to be fluidized by liquid of density 1000 kg per meter cube and viscosity 0.1 pascal second. Assume that the Reynolds number based on the particle diameter is very small compared to 1. If g is equal to 10 meter per second square, then the minimum velocity required to fluidize the bed is this dash. So in this question, rather than calculating the pressure drop, we have been asked to find the minimum fluidization velocity, that is VMF. So we can calculate the minimum fluidization velocity by using this equation. So what we can do is we can equate this term to the incipient fluidization term, the pressure drop at incipient fluidization, that is rho P minus rho F 1 minus epsilon into G. And in the particular question, we have been given that the Reynolds number is very less than 1. That is only viscous term will come into account. So we can only consider this term, and based on solving this, we can calculate this V bar. So we can straight away have the formula for the minimum fluidization velocity, and that is what we will be using to solve this question. So I will just share the video solution. Question number 32 of GATE 2012 Chemical Engineering. A bed of spherical glass beads, density 3000 kg per meter cube, fluidized by assume that the Reynolds number based on the second square and the minimum velocity required to fluidize the bed is dash. So in this question, we have been given a bed of spherical glass beads. This is the bed of spherical glass beads of density. That's what density of the particles or the glass beads is 3000 kg per meter cube. The diameter of the particle is 1 mm, that is 10 raised to minus 3 meters. And this bed porosity epsilon is 0.5. So this is to be fluidized by liquid of density 1000 kg per meter cube. So density of the fluid is 1000 kg per meter cube, and the viscosity mu is 0.1 pascal second. So Reynolds number based on the particle diameter is very small compared to 1. So Reynolds number is less than 1. So if G is equal to 10 meter per second square, then the minimum fluidization velocity, that is VMF, we have to find. So since the Reynolds number is very less than 1, from the Ergens equation, we can write the fluidization velocity as VMF is equal to G upon 150 mu rho P minus rho into epsilon cube upon 1 minus epsilon, then phi square into dp square, where G is the gravitational acceleration, rho P is the density of particle, rho F is the density of the fluid, epsilon is the porosity of the bed, phi is the sphericity of the particles. Since we have been given the spherical glass bits, this will be 1, and dp is the diameter of the particles. So we can replace all these values over here and write it as 10 upon 150 into viscosity is 0.1, density of the particle is 3000, density of the fluid is 1000, and bed porosity is 0.5 whole cube minus of 1.5, 1 minus 0.5 into 1 diameter of the particle is 1 mm, that is 10 raised to minus 3 whole square. So we can solve this numerically, and we will be getting the minimum fluidization velocity as 3.33 into 10 raised to minus 4 meter per second. So we can select the final answer as option A, that is the minimum velocity required to fluidize the bed is 3.33 into 10 raised to minus 4 meter per second. That is option A. So in this question, we calculated the minimum fluidization velocity required to fluidize the bed. Now let's take a look on this question. So this is question number 50 of GATE 2014. So the question states that in a steady and incompressible flow of liquid, density is equal to 1.25 kg per meter cube. The difference between stagnation and static pressure at the same location in the flow is 30 mm of mercury. Considering the gravitational acceleration as 10 meter per second square, the fluid speed is dash. So in this question, we have been given the difference between the stagnation and static pressure. That is delta P we have been given as P stagnation minus of P static. So this is equal to 30 mm of Hg, and then we have been asked to find the fluid speed. So we define the stagnation velocity as static velocity, the summation of static velocity plus dynamic velocity. So the static velocity is usually the same pressure, and dynamic pressure is due to the flow of the liquid. That is, dynamic pressure we can write it as half of rho v square, where rho is the density of the fluid, v is the average velocity of the fluid. Now in this question, we have been given this term P stack minus P, that is equal to 30 mm of Hg. So basically we can simply write this as 30 mm of Hg is equal to half rho v square. And then now using this equation, we can calculate the velocity. But on the left hand side, we have been given the pressure in terms of this mercury head. So we need to change this pressure into relevant units. So we can simply use this rho gh to calculate the pressure and then equate it to half rho v square. So that is, we can calculate this 30 mm Hg as rho gh. So density of the mercury is 13600. Rho gravitational constant is 10. Gravitational acceleration is 10. The mercury height is 30 mm. 30 into 10 raised to minus 3. So this would be our difference of stagnation pressure and the static pressure that has been given. And this will be ultimately equal to half rho v square. Half rho. Now the density, now the velocity that we are considering will be of the fluid of density 1.25 kg per meter cube. So over here the density will be 1.25. And then we will be having velocity square. We can use this equation to find the velocity or the fluid speed. So that is, we did the same thing over here. The pressure difference was given as 30 mm Hg. We calculated the pressure in relevant units by using rho gh and then equated it to half rho v square, and using that we got the fluid speed as 80.79 meter per second. That is, the fluid speed is 80.79 meter per second. Now let's take a look on one last question for the day. So let's take a look on this question number 38 of GATE 2016, in which we have been given that the characteristics curve head capacity relationship of a centrifugal pump is represented by the equation delta H pump is equal to 43.8 minus of 0.19 Q, where delta H pump is the head developed by the pump and the Q is the flow rate through the pump. The pump is to be used for pumping water through a horizontal pipeline. The frictional head loss delta H piping is related to the water flow rate QL by the equation, this equation. the flow rate rounded off to the first decimal places of the water pumped through the above pipeline is dash. So in this question, we have been given the characteristic curve, that is the head capacity relationship of the centrifugal pump. So head capacity relationship is basically the relationship between the pressure head that can be provided by the pump versus the flow rate. So over here, that is, we have been given the delta H pump as 43.8 minus of 0.19 cube. So this pressure head will be responsible for the flow through the pipeline in which we are using this pump. And ultimately, this pump is used for pumping the water through a horizontal pipeline. And then we have been given the frictional head loss, that is delta H piping, as this equation 0.0135 QL square plus 0.045 QL. And then we have been asked to find the flow rate in the above pipeline. So whatever head that has been developed through the pump will be consumed to overcome the frictional head loss in this given scenario. That is, we can say that delta H pump is equal to delta H pipe, and we can equate both of this equation and write this as 43.8 minus of 0.19 Q, and this will become the flow rate outside of the pump, that is 0.0135 Q square plus 0.045 QL. So over here we are having this will simply cube. So over here we are having this simple quadratic equation that we can simplify further as shown in this solution. So we are equating both of these pressure heads of the pump and the piping losses and the head loss due to this friction, and then we are having this quadratic equation. We can solve this quadratic equation to find the flow rate. Since this is a quadratic equation, we will be getting two solutions and we can neglect the solution based on its nature. So one solution will be negative, another will be positive. Flow cannot be negative, so we will be rejecting that and we will be considering only the positive solution. That is, we will be getting the final flow rate for this question as 48.91. So we are simply equating both of this, what the head represented by the head provided by the centrifugal pump and the frictional head loss due to this piping. So we'll be equating both and then getting the solving the quadratic equation to find the flow rate, that is Q. So that was all for today's class. So in today's class we mostly covered the flow through the packed beds, and then we solved few of the questions related to venturimeter, pitot tube, and then this stagnation pressure concept is related to pitot tube. And ultimately then we looked on few this basic question that can be derived from Bernoulli's equation, in which we have to equate the both the pressure losses provided by the pump and the pipe in order to calculate the flow rate. So if you have any doubts in any of the questions or any general questions related to GATE or any of the subjects, you can just write it in chat box, or else we can end today's session. So thank you everyone for joining. We can end today's session.